next speaker is Jose Roman, talking about rational eigensolvers in SLEPc and applications to source-free Helmholtz.
Okay, thank you. This is joint work with Carmen Campos. So I'm going to talk about the rational eigenvalue problems and something that we have been done in the last years. So yes, SLEPc, as you may know, it's a separate library that you install on top of PETC. So it contains several solvers for different types of eigenvalue problems. And here you have the website when you can download the latest version. Okay, so this is a summary of all the type of eigenvalue problems that can be solved with SLEPc. So we can solve problems with one matrix, with two matrices, with symmetric matrix or not symmetric matrices. Even for rectangular matrices, we can compute singular values. So all these are linear problems. And in addition to this, there are a small percentage of applications that need to solve a nonlinear eigenvalue problem that can be of polynomial type. In this case, we have, instead of two matrices, we have three or more matrices, and we define a matrix polynomial. And this is a more general case in which, instead of a polynomial, we have a nonlinear function, t of lambda, that depends on the parameter. So my talk is going to focus on this kind of problems. So this is, all these problem types are implemented in different modules in SLEPc. This is the chart that summarizes the contents of SLEPc. So in this talk, I'm going to focus on the nonlinear eigenvalue solver, and I will talk also about some auxiliary classes that we use for this kind of problems. So I'm going to talk about first define a little bit what's a nonlinear eigenvalue problem and how we interface from the user point of view. Then I will describe a little bit the solver, and then I will go to applications. Okay, so for the nonlinear eigenvalue problem, I have already defined this problem. So we have t of lambda is a matrix valued function that depends on the parameter lambda. Lambda is the eigenvalue. So t of lambda x equals 0 is the eigenvalue problem. And here you can have, you can see a couple of examples. So in this first example, we have a function that is represented in this way, and you can see that this is a linear part, and the nonlinear part in this case is rational. Okay. Another example in which the nonlinear part is an exponential function. So the solvers in principle that we have can solve different types of nonlinear functions. Okay. So since t of lambda is not a matrix but a function, how to define this in a SLEPc program? We have two alternatives. One alternative is to use callback functions. This is similar to SNES, when the user provides a subroutine to compute, in this case, t of lambda and t prime of lambda. So instead of the residual, in this case, we compute a matrix that represents t for a given lambda. And also, in some cases, we need to compute the derivative with respect to lambda. So this is one possibility, but the easiest possibility is when the application formulates or expresses t of lambda in this way. This is what we call the split form. So the t of lambda is expressed as a number of terms in which we have a matrix multiplying a scalar function. Okay? So this is more easy from the point of view of the user, because they just must build the matrices and then indicate which functions are associated with each matrix. Okay? So for this interface, we need to define functions. Okay? So that's why we added a module, Fn, that is intended for defining mathematical functions in SLEPc. So this is quite basic function. It provides a number of predefined functions where the user specifies which type of function and the relevant coefficients. Okay, so with this, we can evaluate the function on a scalar value, we can evaluate the derivative of the function on a scalar value, and also we can evaluate the function on a small dense matrix, which is required in some solvers for nonlinear eigenvalue problems. The functions that we have are rational, and also we have exponential, logarithm, square root, etc. And more importantly, we can combine several functions by addition, multiplication, division, or composition in a way that we can create more general functions. Okay? So with this, we are able to solve many applications that have a nonlinear problem. Okay, so this is actual code for the second example that I showed before. So in this example, there are only 3 terms, and the functions are very easy. So the functions are just minus lambda, the constant, and then this exponential. So this is the code to create the 3 small Fn objects, and then together with the matrices, I pass it to the nonlinear solver. So with this interface, it's very easy to define these nonlinear eigenvalue problems. Okay, how about, apart from defining the problem, I need to define a region of the complex plane where we are interested in the solution of the eigenvalue problem. Okay, so for this, we also define an auxiliary object called RG for defining different types of regions, such as polygon, ellipse, etc. Okay, so this is for the definition of the problem. Now, for the solvers, we have currently 6 solvers available. The first 3 solvers are classical iterations, are very basic, and in the release version, they can compute only 1 eigenvalue. But in the development version, we have added deflation, so they are with this addition, they are more useful because we can compute several eigenvalues. But the most powerful solvers are these 3. We have contour integral solver, we have a polynomial interpolation solver, and also the rational interpolation. So I'm going to focus on this last solver. I'm going to explain it a little bit because it's the solver that is usually more effective for solving this type of problems. Okay, so I'm going to describe briefly this NLEIGS method. So this method is based on 2 stages. In the first stage, we do an approximation, and in the second stage, we do a linearization. Okay? So the idea is that we take the function t of lambda, and we approximate it with a QD, which is a rational function, a rational interpolation. It's like a Newton rational interpolation polynomial. So it's like a Newton interpolation, but the difference is that instead of a polynomial, it's a rational function. So we have a number of terms, the terms, and in each term we have the divided difference matrix multiplying a rational function. And these rational functions here are increasing in degree. So there are a number of factors, and here you can see we have poles and zeros that are defined as Legge-Bagby points from these 2 sets. So these 2 sets, this corresponds to the border, the boundary of the domain, and this corresponds to the singularity set of the function. Okay, so the main problem of this method is that you need to know where your function is singular. So you need to know a little bit about your t function. Okay? So as an example, we have this famous problem. It's called the GAN problem. You can see here is the linear part, and in the nonlinear part we have a square root, and we can see that this function is singular in this branch, and we are interested in computing the eigenvalues in this region. So we pick poles and zeros from here. So the zeros of the function, the approximation are here, and these are the poles. So with this, we can run the solver and compute the eigenvalues that are inside this region. Okay? So this is the approximation. Now the second part is the linearization. So the linearization is done in a similar way as in polynomial eigenvalue solver, which is to build a linear problem of size equal to d times the number of degrees of freedom. So we start with a problem of size n, and we create a linear problem of size d times n, okay, where d is the number of terms of the approximation. That can be very large. It can be like 20 or 30. So these matrices are very, very large, and we must solve a linear eigenvalue problem associated with this. Okay, so once we have computed eigenpairs from this linear problem, we can recover the eigenvector from the nonlinear problem. Okay, so we have implemented this. This has many optimizations in order to reduce cost. So we exploit the structure of these matrices. In particular, when we have to do a linear solve, we do the LU factorization of this matrix implicitly, so that we don't factorize the big matrix, but only have to factorize a block of size n. Okay. Another thing we have is the compact representation of the Krylov basis, and this is to save memory, otherwise it will eat a lot of memory. Okay, so to illustrate this, suppose you have a linearization with degree 6, then you have the Krylov basis expressed as 6 times n, very long vectors. But due to the nice structure of the problem, we can express this in a compact representation, which is a tensorized expression of the Krylov basis. So in this way, it's only necessary to store a Krylov basis of size n together with some coefficients that occupy a little bit memory. Okay, so this is the way we can solve problems that require very large degree of approximation. So the last part of the talk is going to talk about applications. So I'm going to show results of nonlinear eigenvalue problems that are rational. So the functions are rational. In this first application is a collaboration with a group from Institut Fresnel in France, and it's related to photonic structures. Okay? So the application or the equation is the wave equation coming from the Maxwell equations, and here this is an eigenvalue problem where you can see that the permittivity depends on the frequency. Okay, so this is where the nonlinearity comes from. Okay, so for solving the problem, we have to model this as a rational function. There are several possibilities. The easiest possibilities is called the Drude model, where the permittivity is expressed in this way. This is a rational function. And with this, we can formulate a nonlinear eigenvalue problem. In this case, we have only one rational term and a polynomial part of degree 3. So in this case, the number of terms is only 4, so it's not very large. Okay. This is the domain. In this case, we are testing a 1D grating. So we have the solution is periodic in X, it's invariant in C, and also in the Y direction, we have an unbounded domain. So we use the perfectly matched layer technique in order to model the unbounded domain. So this is the periodic boundary conditions, and then the other subdomains. Okay. This is the actual mesh, and in this case, I'm using only 33,000 degrees of freedom. Okay. So with this, we run the solver, and we compute 500 eigenvalues. So these are the computed eigenvalues. One of the goals of this paper was to compare different strategies for discretizing the problem. So here we compare 5 techniques. In 4 of them, we are using the polynomial. So we transform the problem to polynomial eigenvalue problem and solve it as a polynomial. And in the 5th one, we solve it as a nonlinear eigenvalue problem. Okay. So in all cases, the eigenvalues match, except for eigenvalues close to here, but this is not due to the solver, but because of the error in the discretization. Okay. So one conclusion of this collaboration is that there are several ways of solving this problem using nonlinear or polynomial problems, but the nonlinear solver is the most efficient in memory and computational time, and also it's more natural to use because the problem itself is rational. Okay? This application is done with Gmsh and GetDP, SLEPc for the eigenvalue problem, and we are using MAMS for the linear solves. And the second application I want to show, it's very, very similar. The difference is that it's not a periodic structure, but it's related to open problems, okay? Exterior Helmholtz resonance problem. This is a collaboration with people from Sweden, and here we want to study the scattering resonances of metallic nanostructures. And this has many applications, for instance, even in cancer treatment with gold nanoparticles. Okay? So in this case, we have an open domain where we have several scatterers, and we have a planar wave perpendicular to the scatterers. Okay? So we have piecewise constant permittivities. This is, for instance, air, and this may be, for instance, gold. Okay? So the equations are the same as before. Here we are considering TEM polarization and TE polarization. So there are two variants of the equation. In this equation we have the permittivity, and in this other equation we have 1 over the permittivity. So it's also a rational function, but it's different. Okay? Also, in this case, we are using a more detailed model for the permittivity, which is called the Drude-Lorentz model. In this case, the rational function is more complex. We have a number of terms, and each term has 2 poles. In particular, for the gold, we have 6 terms, and it makes a total of 12 poles. Okay. To validate the solver, we first compute the solution of a problem that has, we know the exact solution, which is this resonator with uniform coating layer. And we see that for both TM and TE modes, the eigenvalues computed by SLEPc match the exact solution. Okay? So once that we have validated the solver, we can go to solve a problem that has not, that there is no solution, no exact solution, and we can compute it numerically. Okay? Yeah, so in this case we have, instead of 1 disk, we have 2 disks separated by a very small distance, and in the point of between the 2 disks is where the surface plasmons produce, which is, for certain frequencies we have a peak of energy that can grow exponentially. So for this reason we need a mesh that must be very fine here. Okay? So even if the problem is 2-dimensional, the discretization leads to a problem size which is quite large, about more or less 1 million. And again, the equations. So for the NLEIGS interpolation, we need 15 terms, and these 15 terms come from the 12 poles in the permittivity plus the 3 polynomial terms here. Okay? So this is for the TM, and this is for the TE. The difference between the two is that here it's possible for SLEPc to determine the poles automatically. So the user just provides the rational function and does not care to provide the poles because they can be determined by SLEPc. In this case, since the rational function is more complicated, then we have to compute the poles outside and pass them to the solver. Okay. This is some time, execution time with computing 10 eigenvalues for different numbers of processors. We have more or less good scalability for 128 processors. Of course, we are using MAMS, which has limited scalability. Okay, and some pictures. This is one of computed TM mode, and this is one TE mode where we can see these are the 2 disks, and in the middle we have this surface plasmon that is a big peak in the middle. Okay. So I'm concluding here, just to wrap up, just the take-home message here is that now it's possible to solve nonlinear problems that before it was not possible to do that, and for this we can use SLEPc. So thanks for your attention.
Time for a few questions for Roman.
Yeah.
I may have missed it during the presentation, but why is your NEP solver more memory efficient than your PEP solver?
No, it's
On one of the slides you said it was more time memory.
so do you mean this one? So this representation of the Krylov basis, we have it both in the polynomial solver and in the NLEIGS solver. So this is the same for the two.
And I think it was on slide before.
Here?
It was when you said that the NEP was the best, but I think it's because the polynomial reformulation is more expensive.
Yeah. So it's in this application, yes.
Yeah.
So here we compare the time and memory consumption of the polynomial and the rational one. So for the polynomial, we have to convert the rational problem to a polynomial by multiplying by the denominator. So you get a polynomial of degree 4, I think it is. And then, yeah, so you increase the degree. So it's the computation is quite similar. It's more or less changing one thing to the other, but it uses more memory, but it's for this particular application.
When did you discretize the diagram problem if you what kind of intelligence did you use for the diagram problem?
For the what?
For the diagram problem that you did with SIL2?
What kind of elements? I don't know. I think it's. No, I don't know.
Okay.
So I have a preliminary version of the paper, so I can check it for you. And
Oh,